Okay, welcome back. This is Mr. Hassan's Maths channel, and this is question number 9 from the May-June 2019 Cambridge. This is the AS level Pure Mathematics P1 paper, 9709 syllabus. This question here is about, I guess, differentiation, a bit of quadratics, a bit of a mixture actually. So it says the curve C1 has equation x squared minus 4x plus 7. Another curve C2 has equation y squared equals 4x plus k. So curve 1, as you can see, is a quadratic curve, but curve 2 is not a quadratic curve. It is something which will be like a square root curve. Y will be the square root of 4x plus k if you wrote it. Alright, so now it says the tangent to C, so k here is a constant. The tangent to C1 at the point where x equals 3 is also the tangent to C2 at the point P. So a tangent is a line which has a which is basically has the same gradient of a curve at the point where it's a tangent to the curve, right? So the gradient of the tangent, okay, the tangent to C1 when the point x equals 3 is also a tangent to C2 at the point P. So the gradient of the curve when x equals 3, curve 1, will be equal to the gradient of the curve, equal to the gradient of the curve C2 at the point where the tangent hits it. So let's just try to explain that a bit better. Okay, so you have C1, which is a quadratic looking something like this. The gradient when x equals 3, that's going to be, to find the gradient of a curve, we're going to differentiate this. So let's take this curve, y equals x squared minus 4x plus 7. To find the gradient of this curve, we need to differentiate that. So this will give us the gradient function. So dy dx equals 2x minus 4. That's the gradient function for curve C1. So when x equals 3, the gradient of this curve is going to be 2 times 3 minus 4, which is 6 minus 4, which is 2. So the gradient of the curve, the gradient of the tangent to the curve is equal to 2. So it's going to have a positive gradient, so it's going to be something like this. Okay, so let's say this is x equals 3 at this point here. The tangent to the curve will touch the curve at this point. Okay, and it will have a gradient of 2 at this point. Now the other curve, let's say the other curve is going to have something like, supposing it goes like this, the other curve. Okay, supposing it goes like this. At this point, which is going to be the point P, the gradient at point P is the same gradient as the point here where the tangent touches that curve. They will have the same gradient. They will share the same gradient as each other. So that's kind of like the scenario we're looking at. So we know this is the point when x equals 3, and we can work out what y is as well for this point. We can say when x equals 3, y equals 3 squared, which is 9, minus 4 times 3, which is 12, plus 7. So you have 9 plus 7, which is 16, minus 12, which is 4. So this will be the point 3, 4. This will be the point where the tangent hits this curve, right? And the tangent will hit the other curve at the point P, which we don't know, and we have to find its coordinates. We also have to find the value of k, right? So that's kind of like a little overview of the situation. Okay, it's a little overview of the situation, right? So we need to find the coordinates of this point, the point at which this tangent of this curve at the at the point where x equals 3 will touch this curve here, and we also need to find the value of k, which is part of the equation of this curve, y squared equals 4x plus k. So I'm going to get rid of some of this stuff now and just do the question from scratch. I'm just trying to have a kind of an idea of what we need to do. So I've already actually done some of the things we need to do, but I want to do it in a neater way. Just I wanted to get a little overview first. Okay, so now, what we need to do then is to find the equation of that tangent. If we find the equation of that tangent that we just drew, if you find the equation of that tangent, okay, which is the equation of the curve when at that point where x equals 3, okay, where x equals 3. If you find the equation of that tangent, okay, that's the first step, because that tangent will hit that curve at the point P, so that's going to help us. Okay, so to find the equation of the tangent is going to be something that will help us. Equation of the tangent. Okay, that's what we need to find when x equals 3. Okay, to C1. So what we can do is, again, as I mentioned, to find the equation of the tangent, it's a straight line, we need two things. One, we need a point on the line. So we know when x equals 3, y equals 3 squared minus 4 times 3 plus 7, as we discussed a bit earlier. So that's 3 squared, which is 9, plus 7, which is 16, minus 12, which is 4. So the point 3, 4 is where the tangent hits this curve. So this will be the point 3, 4. This point will be the point 3, 4, where it hits the curve. All right, so it's going to be something like that. All right, and we also know that if we differentiate this expression, so if you have y squared equals x squared minus, sorry, not y squared, y equals x squared minus 4x plus 7. So this is y equals x squared minus 4x plus 7. And we differentiate this, we find the first differential. Okay, that will be the gradient function. To differentiate something, you have to multiply by the power, take 1 from the power. That's 2x to the power of 1, which you write as 2x. And the x term, the x is just dropped, and you're left with the constant. So it's 2x minus 4. That's the gradient function for this curve. So we want to find what the gradient is when x equals 3. So when x equals 3, we can say dy dx is going to be equal to 2 times 3 minus 4, which is 6 minus 4, which is 2. So the gradient of the tangent is equal to 2, and it passes through the point 3, 4. So we can use now the equation of a straight line to find, we can use this formula, y minus y1 equals m times x minus x1, and that will help us to find the equation of the tangent to this curve at the point when x equals 3. So we know y minus the point, y coordinate of the point, which is 4, equals m, which is a gradient, times x minus the x coordinate of the point, which is 3. So we have y minus 4 equals 2x minus 6. We have to add 4 to both sides, so y will be 2x minus 2. So the equation of this line is y equals 2x minus 2. So what we also know is it's going to meet this other curve. I don't know how the other curve looks. I'm going to assume it's going to be like this, but it doesn't really matter. We're not asked to sketch it, but we know that the other curve, which is curve 2, okay, its gradient at the point P will be the same gradient as this line. Or another way to think about it is that the line P will intersect the curve C, will not intersect, it will touch the curve C, it will be a tangent to the curve C at the point P, because we know that when it's a tangent to curve C2 at the point P, so this line is a tangent to curve C2 at the point P. That means it just touches the curve at that point. Okay, so we can understand that if we solve the equation y equals 2x minus 2, and the equation of this curve, which is y squared equals 4x plus k, y squared equals 4x plus k. If we solve these two equations simultaneously, we will find the point of intersection. Okay, that's how you find the point of intersection between two functions. All right, so we can find the point of intersection, but we have two unknowns, but there's going to be something that we're going to consider, because when it's a tangent to the curve, there will only be one solution. So let's see what comes out when we try to solve this simultaneously. So to solve it simultaneously, what we can do is we can substitute one equation into the other. So if I take this y, which is equal to 2x minus 2, and replace the y here with 2x minus 2, I will get 2x minus 2 squared equals 4x plus k. I can square this bracket, which will give me 4x squared. Remember, you square this, then you multiply these together and double it, so that's 2x times minus 2, which is minus 4x, doubled is minus 8x, and then you square the last term, that's going to give you plus 4, and that's going to be equal to 4x plus k. So we can bring the like terms to one side. So you have 4x squared minus 8x minus 4x is minus 12x, and 4 minus k, well, you have 4 minus k equals 0. Okay, so you have 4x squared minus 12x plus 4 minus k equals 0. So what we can understand is, if y equals 2x minus 2, or we can say, as we know, they're told, as y equals 2x minus 2 is a tangent to curve 2 at P, therefore the discriminant has to be equal to 0. The discriminant of this quadratic has to be equal to 0 if, okay, this tangent is a if this line is a tangent to the curve, because the solutions to this will be like a repeated root. It will only have one solution. So what we can do here is we can say b squared minus 4ac has to be equal to 0. The discriminant is 0. This is the discriminant. The discriminant is given by this part of the quadratic formula, which is under the square root sign. If you try to use the quadratic formula to solve, you have minus b plus or minus the square root of b squared minus 4ac all over 2a. This part of the quadratic formula is called the discriminant, because if this is positive, there will be two solutions. If this is negative, there will be no solution. It will be undefined and no real solution. And if this is equal to 0, the only solution will be minus b over 2a. Okay, so if we know that we for sure that this is equal to 0, so we can use that fact, because we know that this is a tangent to this curve. They told us that, so we can use that fact now, okay, to find b squared minus 4ac and equate it to 0, and then hopefully we'll find what k is. So we know a is 4, which is a coefficient of x squared, b is negative 12, coefficient of x, and c is 4 minus k, which is a constant. So if we put this into the formula, we'll have minus 12 squared minus b squared, that's minus 4 times a, which is 4, times c, which is 4 minus k, and that has to be equal to 0. So we're going to have minus 12 squared, which is 144, minus, you're going to have 4 times 4, which is 16, so minus 16 times 4 is minus 64, and minus 16 times minus k is plus 16k equals 0. So 144 minus 64 is actually 80, so 80 plus 16k equals 0. 16k is equal to negative 80, which means that k is equal to negative 80 over 16, which I think is 5. 5 times 10 is 50, 5 times 6 is 30. Yeah, so it's going to be negative 5. So k is equal to negative 5. So we've answered one part of the question, and we also have to find the coordinates of P. So to find the coordinates of P, what we can do is we can use the fact that this equation will be, okay, the equation of which will tell us where the two curves, the curve and the line intersect. Where this curve and this line intersect will be determined by this equation. This equation is basically the this will tell us the solution, tell us what the x values are of where these two intersect, because we solved these two simultaneously and we ended up with this. So now we know k is negative 5. So if I replace k equals negative 5 into this equation, we can find the x value of where the tangent hits the curve. So 4x squared minus 12x plus 4 minus, be careful here because this is a minus 5, so it's 4 minus minus 5 equals 0. So you have 4x squared minus 12x plus 9 equals 0. Now to solve this equation, what you should understand is whenever you have a equation formed when a tangent, a line is a tangent to a curve, it will always be a perfect square, because you're going to have what's called a repeated root. And we can see the first term is a perfect square, 4x squared. The last term is a perfect square plus 9. So even if you're not sure if it will be a perfect square, you can, if you ever spot the first and the last term in one of these quadratics being a perfect square, and then you have a middle term, you can think, is it going to be a perfect square? So you take the square root of 4x squared, you write it here as 2x. you take the square root of 9 and you write it here as 3, and you write the sign. If there's a plus here, you put a plus between them, and minus, you put a minus between them, and then you square that bracket, and then you ask yourself, from the pattern that we learned for expansion, does it give us the correct middle term? So when you expand a square bracket, you square the first term, 4x squared, square the last term, plus 9, but the middle term is always the product of these two doubled. So 2x minus 3, 2x times minus 3 is negative 6, doubled is negative 12x. So we know that this is definitely the correct factorization of that, right? If we expanded this, we're going to get 4x squared minus 6x doubled minus 12x and plus 9. So then we can say that means 2x minus 3 is equal to 0, which means x is equal to 3 over 2. So that's the x value of the point P. The x value of the point P is 3 over 2. Now what's left for us to find now is a y coordinate of the point P. Now we could use either of these two equations. All right, we have y squared equals 4x. Now we know k is minus 5, so this is now going to be y squared equals 4x minus 5, right? But this is of course easier to use. You don't have to worry about square rooting and stuff. So we replace the x in this equation. So we say y equals 2x minus 2. So y is going to be 2 times 3 over 2 minus 2. So y is going to be, they cancel out, you're left with 3 minus 2, which is equal to 1. Okay, so we have the coordinates of the point P, 3 over 2 and 1. Okay, so there is the answer to this question. Now somebody might have done the following. They might have put the answer in here, 4x minus or plus k. So you'd end up with 4x, y equals 4x minus 5. Y squared equals 4x minus 5. Now if they put the x value in here, they'll have y squared equals 4 times 3 over 2, okay, minus 5. So you'll have y squared equals, that will be 6 minus 5, which is 1. And they might write the answer y equals plus or minus 1. Okay, and that would actually not be actually a correct answer. All right, so you can see here from here y is equal to just 1. It's not going to be plus or minus 1. So you should not use the square version of this. Okay, so if you did, for example, found y equals minus 1, and you use y equals minus 1, and you use that to find the x value, then you would have, it wouldn't really be correct, okay, but the mark scheme condones that. They condone that, right? So if you ended up with y equals minus 1, and I think it was x equals a half if you use y equals minus 1, then the mark scheme actually says it condones that, but you should, okay, go with the answer x equals 3 over 2 by solving this equation first, and then finding when your x equals 3 over 2 in this, you get y equals 1. Don't put it back into this equation here, okay, with the squared. All right, so that's something that you should be aware of. All right, so you should put it into the linear equation. It's always sensible to put in the linear equation anyway, okay, because it's easier to use. All right, so especially with these curves which are y squared equals, they end up being curves that look like this, which are not actually functions unless you have limited the them to the positive square root or the negative square root. That comes later. That comes in functions later on. All right, or whenever, it depends when you're doing this question, but that's something that comes later. So always replace, okay, like here we found the value of x for which this is true, and replace that always in, if you have a choice, always replace it in the linear. So you know that when x equals 3 over 2, y is going to be equal to 2x minus 2. Okay, the y value you get from this and the y value you get from that will be the same. Okay, the y value you get from these two will be the same. The reason why we get two different y values for this is basically because when x equals 3 over 2, this is the line x equals 3 over 2, they intersect in two places. Okay, it will intersect the curve, this curve, because this curve, y squared equals something, will look like this. It's not actually a function, because it's called it fails a vertical line test. It's like one x value goes to many y values, so it's not a function. So it's going to have two outputs for every input. As you can see, it has two outputs. For when x equals 3/2, you have two outputs, plus 1 and -1, right? So we know that we want to find when this line intersects with the curve, and that is when x equals, as we find when we put x equals 3/2 in here. Okay, we know that the point is when x equals 3/2. When we put x equals 3/2 into here, it's going to give us the place where it intersects with this line. Okay, here it gives us two values. The place x equals -1 is not one of them. That's the place over here. So for example, y equals 2x minus 2. Let's say this is over here, when y equals 1. All right, the other place where basically x equals 3/2 is going to be over here. That's not where you will get the correct y value. This will tell you the correct y value. All right, so this when you use this equation, you get two answers, plus or minus 1, but we're concerned with the answer we get from where it hits this line. This will tell us two places for y when x equals 3/2. We want to know what y is, okay, when x equals 3/2. Where does this line hit this curve? So we can't be sure from this. It could be either of those two places. From this, we can be sure that when x equals 3/2, y is going to give you the correct value, which is 1. So the coordinates of P are 3/2 and 1. So I hope you understand why in the mark scheme they have like alternative answer, and they say condone that answer, meaning they will overlook the fact that it's actually not the right answer, but because your equation comes out with plus or minus 1, they might condone the fact that you found plus or minus 1, where in fact you should use this line. This gives you the answer. This gives you two possible places. Okay, for y, this gives you the place that we want. So I hope that was clear. It's a bit of a small point that you have to consider in this type of question. There are alternative ways of solving such a question, using the gradient function for this as well, but I think this is by far the simplest way of dealing with it. Okay, so you basically, what the overall look was that at the point x equals 3, there's a line which is a tangent to the curve. That same tangent is a tangent to the other curve at the point P. We have to find the equation of that point P and this constant in the curve, the second curve, which we don't know. So we find the equation of this tangent, which is a tangent to both curves at these different points. And once we found the equation of the tangent, we know that this tangent touches the other curve at this point P. So if I solve simultaneously the equation of the tangent and the equation of that curve, I know that I will end up with one solution, a repeated root, which means when I try to solve this simultaneously with that, if I substitute this into the y here, I'm solving them simultaneously. This has to have just one solution. So when you rearrange it, you know that b squared minus 4ac has to be 0, which leads you to find that k equals -5. Once you found k is -5, you can now basically work out the point of intersection. This equation tells you where they intersect. So replacing the k with -5 gives you this equation, which we then solve for x, gives us x equals 3/2. Substitute that back into the equation of the tangent, okay, because that will give us a single answer for y. It won't be ambiguous. And then that gives you the y coordinate of the point, and we've now found what k is, which we had to do, and we found what p is, the coordinates of p. Alright, so other questions from this particular paper will be found in the playlist that will appear in this region of the screen at the end of the video. Other questions from this topic of, I'm guessing I'll put this under differentiation, which will be in this region over here, the playlist for differentiation from the Cambridge collection of P1, and I'll also put it under the Quadratics playlist as well, because it's got some stuff to do with the discriminant. It's a bit of a mixed up question, different topics in there. And you can subscribe to my channel by clicking on this link up there. Thank you for watching, and see you soon.